Yeah, so this review is going to be covering all of the aspects of fatigue design. We're going to try to do it in 1 hour because we want to put things in perspective. So as you know, in fatigue design, we have 3 different methods. And these methods are shown here. Is either that we have a strength-based, 2 different methods based on the strength, and then a third one that is based on fracture mechanics. The strength-based methods, one is for low cycle fatigue. If the number of cycles is roughly below 1,000, then we use a strain-based approach. So we have to find the elastic strain and the plastic strain and use a correlation that gives us the relationship between the applied strain and the number of reversals to failure. And this method is used for advanced design because we need to be able to calculate the plastic strain. And that's not what we covered here in the class. So the other strength-based method is the standard SN method that we emphasized. And that is the applied stress range versus the number of cycles. And the applied stress range means the amplitude for a fully reversed load as a number of cycles. So that's the second method. The third one is fracture mechanics based, and we have a correlation based on data, experimental data, and it's put into the form of an equation called the Paris equation that tells us the rate of growth of the crack as a function of the number of cycles. So we're going to kind of review fracture mechanics and the SN method and give a few applications. For fracture mechanics, the idea is to find the stress intensity factor around that crack. And the crack size is 2A. So the stress intensity factor is a shape factor beta, which depends on the crack dimensions in relationship to the sample dimensions, and we have tables and charts for that. So beta is a function of the crack size divided by some kind of measure of the sample size. And therefore, as the crack changes size, then beta changes as well, and that can cause some difficulties. And the stress is the remotely applied stress, not at the crack tip, but remotely, meaning average stress or nominal stress without the crack, away from the crack. So that's kind of the stress intensity factor. We know that immediate fracture happens if the stress intensity factor is greater than the fracture toughness. And we know the fracture toughness of the material. We can use it. It's a material property. Just like what we use the yield, the strength of the material, we have another property called the fracture toughness, and the units would be MPa square root of meter or KSI square root of inch. So that's kind of the threshold. If K1 crosses that threshold, then the crack will immediately propagate and immediate fracture happens. Now for fatigue, the crack starts at very, very small size. So the stress intensity factor is much, much lower than the fracture toughness. However, with every cycle, the fatigue grows as a function of delta K. Delta K is the applied stress intensity factor range. And that means that it is beta times, instead of sigma, it will be the value of sigma max minus sigma min. That's kind of the applied range times the square root of pi a. So in this case, if we know a fluctuating stress, as in our project and the connecting rod project, we would know at a critical location. We have to choose a critical location for the crack at the fillet or at the contact area between the connecting rod and the shaft, or in the middle of the connecting rod. So these are a few. We have to select a few locations, and these few locations we compute from COMSOL the delta sigma that is up that results from the calculations. It's all elastic here. So the delta sigma that results at these locations, and then assume that there's an initial crack size that is going to grow. So as it grows, the rate of change of the crack size with respect to the number of cycles is a constant times this delta K raised to another constant. So these two constants are material data, come from many experiments. And for example, for ferritic martensitic steels, the C constant is about 7 times 10 to the minus 12 in the units of MPa square root of meter, and the exponent M is 3. For martensitic steels, it's a different number. For austenitic, it's a different number. So we have those available for us. If we're using an aluminum or alloy, or using a titanium alloy, then we must find that information from the literature to be able to determine the crack growth rate. And the way that we would do it is basically we have a first order differential equation, dA by dN, and we solve it either analytically or numerically. The way that is solved is very easy. You separate the variables and you integrate from one side dN, the other side is dA divided by the product of C times beta delta sigma pi square root of pi a to the power m. So this function underneath dA is pretty much constant if delta sigma doesn't change. In other words, if the cycle keeps repeating the same way. The only issue is if the crack grows, then beta can change. But in some practices, we see that the change in beta is very small over the number of cycles if the crack doesn't grow too much. And therefore, the problem becomes very easy because we can pull things out of the integral and integrate from an initial size to a final size. If for a problem, a homework assignment problem or an exam problem, we have to assume beta as an average value, like we could determine an average value or given that value, and therefore the integration will be pretty straightforward. So integrate dA divided by square root of a to the power m, and everything else is constant. And the only problem is that we have to figure out what is the initial size, what is the final size. The initial size is very well fixed by the NDE inspection method used. So if we have non-destructive evaluation, for example, an acoustic method, then we can detect a minimum crack size, let's say on the order of 10 mils, 10 thousandths of an inch. And that could be done on a massive scale of when they produce and manufacture connecting rods, and they have to inspect acoustically every one of them to see if there's any crack that is above that value. If we have a very expensive component, we can even use X-ray techniques to map it out and find the minimum crack size. But that can become expensive, and we can eliminate components that have larger initial crack size. So the main thing now is that we have to make reasonable assumptions on the available initial crack size based on the inspection technique that is used, and that would be fixed. And then we integrate up to a maximum crack size. So the maximum crack size, as the crack grows through the material, is going to propagate, let's say here. So if I have a crack that's going to start here, is going to propagate. And as it propagates, let's say in this example, I have an applied moment M that is oscillating, and the crack keeps moving up, up, and up, and up. Obviously, when it goes to a certain critical size that we have here, this size here, A final. So A final here is going to be a value beyond which the crack cannot be stopped. In other words, it will be gone. So the question is that how do we find the A final? And for us, we have to test two different possibilities, and that's important. One possibility is that the crack can propagate in a brittle fashion, and that is if the stress intensity factor is greater than the fracture toughness. So for this A final, we can determine it from the condition that the stress intensity factor is equal to the fracture toughness. So that's one checkpoint that we have to do. The other one is that the remaining ligament here, this piece here, may not be big enough to support the applied load, and it could lead to yielding. So the applied load, even though the crack is not, the stress intensity factor of the crack is not larger than the fracture toughness, but the remaining ligament is so weak that it can just tear apart in a ductile fashion. So we have to have another test, and then the other test is that we ask ourselves what is the stress in that remaining ligament, and is it greater than the yield strength of the material? And that's what we have in this example. So we have an example that has the ultimate strength of the material is given 185, and the moment is from 0 to 1200 pound force inch. The yield strength is 170. The K1C, this is a fracture toughness, plane strain fracture toughness, is 73 KSI square root of inch. And the C factor is given, and M is 3. And the initial crack size is given to be 4 thousandths of an inch. And we want to find the number of cycles to failure. So for this problem, the loading conditions are given in the simplest possible way, meaning that we have we avoid doing extra calculations on statics and conversion of statics to load and load to stress and so forth, because that's another issue, right? So here we just have M, and the stress will be tensile or compressive, bending, My over I, MC over I, and then we can compute I over C for first here as, excuse me, BH squared over 6. And we'll compute delta sigma, which is delta M divided by IC. And we find now the delta K. So we can compute delta K from delta sigma. But before we go on to do the integration, we have to find the final size of the crack to which we're going to integrate. So if we assume that it's going to be brittle fracture, and the telltale here is that the yield strength of the material is kind of close to the ultimate, so there's not a lot of ductility once the material yields. So most likely it's going to be brittle failure, but we have to check. And we don't have any information on beta, so we're going to assume beta equals 1 for the time being, and find the final crack size to be the K1C, like we assume K1C is equal to the pi square root beta. It will be, if we just take that here, we take the square root of both sides. So it will be beta sigma max times square root of pi a. That's equal. So from that we solve for a final and find a final to be 0.1278 inch. So the crack is going to propagate under this assumption from 0.04 of an inch to 0.128 inches, and the propagation is going to follow this equation here, the integration. If we assume beta equals 1, we can pull it out, and the integration is rather quick once we figure that. And for this, we can find the number of cycles to failure. Here we can do some more iterations. In other words, if we start, and then we go to the figure 527 to determine another value of beta, and that gives us another final value for the crack size, and therefore we can estimate this a little bit better. So for your project, the easiest way, of course, you have time now. This is for solving a homework assignment problem, or for the final exam. We would have a constant beta, we'll pull it out, and then do the integration to get that number. For the project, the best way is to use a numerical method. So if you have a MATLAB program, we can just call a numerical integration function like ODE 23 or 45, one of these functions that they have in MATLAB, and you write the differential equation and it will solve it for you. Or you could do it poor man's way, that step by step, delta A in step J. You fix the delta K, so you write a program by yourself, and then you increment the crack size and you increment the number of cycles. But this is really poor man's way. But so we could just use MATLAB to do the integration for us. And what we do in the project is that we have to go find beta from the charts and fit an equation to beta as a function of A, and then we can put it inside here and then do the integration numerically, and that would be guaranteed to give us the right solution. So this example relates to how you're going to apply fracture mechanics to analysis of the number of cycles to failure for the connecting rod project. So to summarize, you have to find 2 or 3 critical locations and find the stress amplitude, and then find from NDE the minimum crack size that you will assume, and then find the corresponding constants in Paris equation. If you're using 4130 steel, then we have it in Shigley. If you're using titanium or aluminum or other materials, then we have to get this information from the data sheets. And then you do the integration. And here, what I found is that I get a lot of questions later on that the number of cycles from fracture mechanics is so much lower than from the strength-based method, which is SN method. And there are reasons for that. One of the reasons is that if you have a compressive load, so a cycle can go tension, compression. So if you have a compressive load in the compressive part of the cycle, the crack doesn't grow. So in the connecting rod, you have to watch for that. You see only in the tensile parts that the crack can grow. The other issue is the minimum size. The result of the number of cycles is really sensitive to the minimum size. And therefore, we have to look at maybe more better inspection techniques to go to lower and lower minimum size. And then the third that comes in is the units. So a lot of times the units are confused and then you don't get the right answer. So that's my review of fracture-based method. Now the third method is the SN method, and we're going to give a quick review and a couple of examples on that. In the SN method, we have a diagram basically on a log plot and log to the base 10. So the vertical is the applied amplitude, so in a fully reversed fashion. In other words, the average stress is 0, so you have up and down around the 0, and the amplitude is plotted here, S, and here is N in log to the base 10. And the graph is typically a bunch of points from data, and then we fit a curve to that. But for just rough design purposes, we divided the graph into 3 linear regimes on the log-log plot. And linear on the log-log plot means power law on a standard linear scale. So we have 3 regimes. One is low cycle and from A to B, and one is high cycle from B to C, and one is endurance, infinite life, from C on. For the connecting rod, we hope that we can go to infinite life. So the requirement is that the amplitude is going to be below the endurance limit. For other applications, we like maybe the gear application or the gearbox reducer, a speed reducer, we could end up having a low cycle application or a high cycle application. So the main idea is to find the coordinates of these 3 states, A and B and C, and the coordinates on the log-log plot. So the coordinate of A, the X value is 1 cycle, and the Y value is the ultimate strength. So if you go in 1 cycle, you just pull the material to its ultimate is going to break. That's clear. The state B is the end of the low cycle fatigue state defined by 1,000 cycles. So the x-axis has 1,000, and the y-axis is a fraction of the ultimate. So it's not exactly ultimate, but it will be lower than the ultimate. So this fraction, there's kind of a method in the book to determine F from the strained life method, which we kind of not emphasize here, or from empirical charts. So we have a chart also to find this fraction F. So there's this method here from strained life method. If we know the fracture strength, and we know the exponent B and the epsilon versus n versus 2n curve, the Manson-Coffin criterion that we did not emphasize because we just lack of time that we can do plasticity, we can find this F. So for us here, we would just assume that F is given or is obtained from a chart. And we have a chart in the book to give us F, the value of F as required, as a function of S ultimate. So we have now the y coordinate of B is F times S ultimate. So F could be 0.8, 0.9, 0.75, in that range. The last point here, C, has a coordinates of, by definition, of 1,000,000 cycles. Beyond 1,000,000 cycles, technically, we say this is an infinite life. So we have here the x-axis has 1,000,000 cycles, and the y-axis has a value of the endurance limit of the material. And the endurance limit of the material is, again, another fraction of the ultimate strength. In other words, people are just trying to say that if I know the ultimate strength, then I know everything about that material. That's kind of the story. So the ultimate, if you have a steel, the endurance limit is roughly half of the ultimate. This is kind of empirical. And therefore, if I know just one number, which is ultimate, I multiply it by F, I get the Y coordinate of B. I multiply it by 0.5, I get the coordinate of C. And in between, we have two straight lines. AB and BC are two straight lines. And the two straight lines on a log-log plot mean that they are power laws. So for the high cycle fatigue side, which is B to C, we write S equals A times N to the power M to the power B. These are different B's from before, different A's. And A and B, you just find them from solving the straight line, and it has the coordinates B and C. And the result is given to us. A is given as F S ultimate over S endurance, squared over S endurance, and B is minus 1/3 log to the base 10 F S ultimate over S endurance. So that is what we have here, and therefore we can use this to find the number of cycles of failure, given that we have fully reversed. And I'll talk about what happens if it is not fully reversed in just a few minutes. For the low cycle fatigue, I have a curve from A to B, which is a straight line on a log-log, which is again a power law on linear. So it's F is a constant. The constant, instead of A here, it becomes S ultimate. And the B, the exponent, becomes log F over 3. So it has the same form as the high cycle fatigue, but two different constants that we can obtain. So I will now look at a quick example that I have steel 1050, and I want to find the endurance. I want to find S at N equals 10,000 cycles, and I want to find N for S equals 55 fully reversed. So quickly we get from the table, we get S ultimate 90, and we get S endurance to be half of that, 45. We get F from this correlation or from figure 618, and it comes to be 0.86. And therefore, from that, we are able to find the constants for that control the relationship between S and N. That is to say, S equals A times N to the power B. So A is F S ultimate squared over SE, 133.1. It has units of KSI. And B is 1/3 log of F times S ultimate over S endurance. And that gives us a negative number, minus 0.0785. And therefore, I got my correlation completely resolved here. So you can see it here. And that, therefore, it will become, the task is that if I give you N, then you plug it in, you get S. If I give you S, you plug it in, and they get N. And these are the two things that happen in this particular example. So now I move on to what happens in real life if I have the material different from the sample. As we know that the standard sample is very highly polished, and we use the rotating beam technique to get S endurance. And we say that, roughly speaking, S endurance is half of the ultimate, or some other fraction. If we have a titanium, or if I have another aluminum alloy, it will be different from half. The half is for the steel. And then I'm going to practice. I'm using this in an application. So the application will have different surface finish from the sample, different size from the sample, different loading condition from the sample, different temperature, and maybe some other factors like corrosion, erosion, residual stresses, many different things. So in practice, it becomes more reliance on experimental data and correlations. And for us, the standard design procedure is to say that the endurance limit is a knockdown of the endurance limit of the rotating beam sample. So rotating beam sample, we put it prime, so that's E prime, that's half of the ultimate. And then we start knocking it down with 5 factors here. One is surface factor, and we have tables for that, depends on the surface condition, ground, machine, hot rolled, as forged. And the second is a size factor. We have a correlation. And then the third is a load factor, either 1.58 and so on, correlation. And then the temperature factor is the ratio of the strength at a given temperature divided by the strength at room temperature. That's again a fraction. Reliability factor, it is usually 0.5 for 100% reliability, meaning that this, you have to, it's like having a higher factor of safety, basically, if you have a 0.5. And if you accept different levels of probabilities, then reliabilities, then you can use a larger fraction. And then the other factors, they depend if you're working in a company that have its own experimental data, then you have to put that data in a format that you have a factor coming, depends on the corrosion or erosion or any of the environmental effects. So we kind of have a modification of the rotating beam endurance limits here. The other is that when you're going to go to a shaft, the shaft, of course, is going to have different sizes, right? Like in our design project. So we have to use the corresponding size factor, and the surface finish will be different. It'll be ground and machined or honed, depends on how expensive the piece is. And therefore, we could apply all of these factors, right? But there's one more thing. One more thing is that the shaft is always stepped because we have to put attach the gears to the shaft. And at the shoulders or in the retaining ring, that we have to put a groove for the retaining ring. At these locations, we have stress concentrations. So we study stress concentration factors if we have a static load. If we have a fatigue load, the situation is not so bad because the stress concentration factors become less severe. In other words, we have a stress concentration factor. We get it from the charts for the stress concentration factor, and we're going to call these KT. This is for static, theoretical static loading. But for fatigue, what happens in fatigue is that locally, the stress is so high that you get plastic deformation, and plastic deformation kind of relaxes the stresses. So the effective stress intensity factor kind of goes down, and that is expressed in what is known as the fatigue notch sensitivity factor. So the notch sensitivity factor Q is the deviation of K fatigue from 1 over K theoretical from 1. In other words, we can obtain KT from the charts, and if we know the value of the notch sensitivity factor depends on the material, then we can determine immediately the fatigue, the stress intensity factor under fatigue conditions. So for the Q, we have a plot in the book, equation 635A or 670B. for Q that has a polynomial in the value of the notch radius A. So it depends on notch radius. So if you have a retaining ring, the notch radius is going to be extremely small, so the stress intensity factor will be high. If you have a shoulder, the notch radius, you can actually taper it, therefore the stress intensity factor will be low. So we have a correlation by a polynomial in these equations and charts that give us Q as a function of the notch radius. For example, if I have Q equals, if I know the Q value and the K sub T, then I can find now the K sub F that I use in my shaft design. So I need that actually to design the assembly for the speed reducer project that we have. So now I will shift on to what happened when we have a stress that is not with a zero average. So a stress that has a shift. So if you have a stress cycle that has a mean value that is different from zero. So in this case, the idea is that the fluctuating part causes damage by itself that we know about as fatigue. And the steady part, which is the mean value, causes another form of damage. And then we combine them together so that the total damage function does not exceed 100%. So we're going to define a damage fraction based on the value of the alternating stress and another damage function based on the value of the mean stress. So let's talk about it. The mean stress, as it gets closer and closer to the yield, it means that the material is going to actually yield. Therefore, a reasonable fraction is the ratio of the mean stress divided by the yield stress. That's the ratio. So if this ratio is 100%, then we don't have any chance to even sustain any fluctuating load. So we're going to define a damage fraction to be the ratio of the mean divided by the yield. The same thing we could do is that we have a damage function, which is the ratio of the value of the alternating stress divided by the endurance limit if we are designing for infinite life, or divided by SF if we're designing for a finite life. So it depends on whether we're designing for endurance or we're designing for a finite number of cycles. We choose the corresponding value a material value, either SE or SF, and use it. So this approach has been tested and used in the industry, and many correlations have been assumed for these because these are all experimental. The surviving ones are 4 that we studied here, and these 4 are shown here. So the Soderberg is sigma alternating over S endurance plus sigma mean over S yield equals 1 if you are certain. If you want to include a factor of safety, then you say 1 over N, where N is the factor of safety. So this is called the Soderberg, damage due to fatigue plus damage due to the steady load equals 1 over N. This is a linear relationship where if I plot on the vertical sigma alternating over SE, on the horizontal sigma M over SY, I get a straight line. So the straight line that you see is this one, the lowest one here. So this one goes from S endurance to S yield. So this is a Soderberg line. There's another relationship that is more forgiving, and that is another linear relationship that we can see here, where the mean stress is assumed to even go beyond yield. So you accept some hardening. You accept that plasticity is going to be okay. So in this case, the mean value of the stress can have a maximum limit of the ultimate instead of the yield. This straight line is called modified Goodman. So we have two straight lines, Soderberg, modified Goodman. So modified Goodman is same thing, same structure, but instead of yield, it becomes S ultimate here. Now, other experimental data coming from the automotive industry mainly gave a little bit more range for design. And instead of using straight lines, the correlations use a parabola. So we have two parabolas. One is the ASME, ASME, actually it's an ellipse, so ASME, and that has a curvature, as you can see here, and it goes from S endurance to S yield, so it is expanding Soderberg. And then the other one is Gerber, which is a parabola, and again, it expands the modified Goodman. So Soderberg linear, modified Goodman linear, then the ASME expands Soderberg, and the Gerber expands the modified Goodman. So it means that you have, for the Gerber, you put a square on the last term here, and in the ASME you put squares on both, the damage for alternating and the damage for the steady loading. Okay, so this is all very nice, but there's one more consideration, is that if the amplitude is very large of the fatigue cycle, there's a potential possibility that on the first time I apply the load, let's say that I have the mean is very high, let's say 70% of the yield, and then I apply a load here that is going to go up and up and up and then go down again. But as it's going up and up and up, it's very possible that the actual stress, which is the mean plus the alternating, will exceed the yield on the first cycle. And we don't want to do that. So there's one more constraint on the problem, and that is to use a line called the Langer line. And the Langer line is here. It goes from S yield to S yield. This one here, it means that the sum of the alternating and the mean shall not exceed yield at any point. So whatever we do, we have to be below the Langer line, because that means that on the first cycle or second or whatever cycle, then if the sum exceeds the yield, then the material is already plastically deforming, meaning that it's going to ratchet from one cycle to another, and is going to build cracks in it. So these are the design considerations that we have to take, and I wanted to show how we consider that. So for example, if we have modified Goodman as a criterion, we usually have a load line, and the load line is the ratio of the alternating over the mean stress. In other words, if I'm applying a load from outside, it produces an alternating stress, and it produces a mean stress, like let's say a moment plus an axial load, or a moment, let's say. And as I increase the value of the moment, if the moment is caused, let's say, by a force that is off axis, and take this example, as the force increases, both the moment will increase and the axial force will increase proportionately. So everything is going, whether the mean or the alternating, are going to be increasing in proportion to the applied load. And therefore, in design, we always look for something called a load line. A load line is the ratio of the alternating divided by the mean. and that ratio gives us like a fraction. So as the fraction is constant, and we're looking for that load line. So if we are looking for a relationship, let's say in this case, this is an example. This is the alternating on the vertical, and the mean is on the horizontal. Then we have a straight line that that's called the load line. So as the load increases, both the value of the alternating and the mean increase in proportion. So the load line, at some point, increasing the load will cross the Langer line here and will cross the Gerber line, for example. And therefore, we have to see if we have a load line, will the yield come before fatigue? Or if the load line has a different slope, will the fatigue come before the yield? And that's the example that we have here. We have an example, and the example has modified Goodman. So first, to talk about modified Goodman, then I'm going to talk about Gerber in a minute. So if it is modified Goodman, we have a linear equation for S alternating versus SM, and the load line, which is another straight line, S alternating with SM. And we solve for these two together by taking, eliminating one of them, one of the variables, putting it here. And the solution gives us intersection point. And this intersection point is the allowable alternating and the allowable mean right here. And as I said, we have to guard against yield, and we have to do the same solution all over again, but the load line now solved with the Langer line. The Langer line is S alternating over S yield plus S mean over S yield equals 1, and we solve for that, we get the point. So that's kind of a procedure if we have two straight lines. Now this example is a procedure where we have one straight line, the Langer, and the other one is a parabola, which is a modified Goodman. So we have 1.5 inch diameter IC 1050 load from 0 to 60 kip. So it fluctuates from 0 to 16 axial. And it has a fatigue stress intensity factor, 1.85. Then we want to find the alternating S alternating SM and the factor of safety for fatigue and factor of safety for yield using Gerber. So it is more like a graphical problem that we want to solve. First, we go to find the S ultimate, S yield, find the alternating value of the force, because the force is from 0 to 16. So the average value of the force is 8, and the alternating component is 8. So we have FA, FM equals 8. And we know the diameter, and therefore we would know the stresses, right? The alternating and the mean. And then on the other side, we have to put the problem into two columns. One is material properties column, and the other one is load column. So material properties, I have to compute from S ultimate everything else. The fatigue factors, Ka, Kb, Kc, and so on, so that I can find the endurance limit. And then from the load column, we find the sigma alternating and the sigma mean. They are equal to each other, 4.5 KSI. And we apply the same fatigue factor that we found here. In more complex problems, then we have to look for the notch sensitivity factor, convert the theoretical stress intensity factor to a fatigue intensity factor, but here is given to us as 1.85, and we apply it to the values, and that's basically what we're going to do in the design for the shaft design of the gearbox. So we have to find KF for every location, And therefore, if we're looking for Gerber, then we have to solve a parabola with a straight line. So the straight line R equals SA over SM, and the parabola is given here. This solution, you don't have to do it even, because you can solve it by yourself. You can put this into here and solve a quadratic equation, but it's given to us in the book. So the book has a table that has the solutions already. So this table gives you SA in terms of S endurance, S ultimate, R. The R is the slope of the load line. And the fatigue factor of safety is the ratio of S alternating over sigma alternating in here. So that example looks like here, where we have from the yield stress was 84 and 84, so the Langer line is going from 84 to 84. The load line is actually turned out to be that one. So what's going to happen is the actual operating point is at 8.4 and 8.4 in terms of the alternating and the steady stresses. And you can see this point is far away from any danger, because the first time the load line is going to meet the fatigue limit first, and then as you continue the load, you're going to meet the yield limit. So this situation can result in fatigue failure before yield. And the factor of safety would be the ratio of the intersection point, which is here, this intersection point, divided by the actual point. And since it's linear, you can take any ratio. You can take alternating or mean over mean, or you can measure it here on the straight line. But usually we just use one value, like you can take the vertical and then take the ratio of this vertical divided by that by 8.4, and that gives us the safety factor. Now, in case we have a finite life instead of infinite life, like all of this designed for infinite life. If I have finite life, I have to replace the S endurance by the sigma, or I have to replace sigma alternating rather by another equivalent stress that's called sigma REV, sigma reverse, like an equivalent fully reversed. The equivalent fully reversed is the alternating stress, but it is divided by 1 minus sigma m over S ultimate. This is the relationship that reflects the amount of damage due to the mean stress. So you kind of subtract the amount of damage due to the mean stress, and therefore the equivalent fully reversed stress could be higher, could be substantially higher than the alternating stress, because you're kind of subtracting the damage due to the mean stress. This relationship is based on Soderberg, because Soderberg tells you that sigma alternating over sigma fully reversed plus sigma m over sigma ultimate is equal to 1. Sorry, on Gerber, not Soderberg. If it is S ultimate, it will be Gerber here. Soderberg should be S yield. But based on that relationship, I have fully reversed, converted the sigma alternating into a fully reversed, and then I use now this value in all of my calculations regarding finding n given sigma, or finding sigma given n. The same story as we did before for a fully reversed stress. We can use it here after we make that correction. So the idea here is to enhance sigma alternating by subtracting some kind of damage from 100%, and that damage depends if you use Soderberg, it will be sigma m over S yield. If you use modified Goodman, it will be SM over S ultimate. Next is that what happens if we have multi-axial loading, as we have in fatigue and shaft design, like in next chapter be shaft design. The idea is to use distortion energy theorem. And distortion energy theorem is we replace every stress by the von Mises equivalent. That's it. So if I have a maximum stress, I find the corresponding von Mises. Von Mises would be sigma alternating plus sigma mean. That's the maximum stress. So it would be squared plus 3 times tau squared. Like this is the von Mises to the 1/2. This is a von Mises formula if I have only axial and shear stresses, right? So this is like sigma squared plus 3 tau squared. The sigma is the maximum and the shear is the maximum. And then I can find the minimum, and therefore I can find the alternating as the difference between the maximum and the minimum over 2, and I can find the mean as the maximum minimum plus the average value between maximum and minimum to use it. So to summarize, 2 important things. If I have non-zero mean, I have to correct the alternating stress and enhance it and call it sigma REV and use that in SN type calculation. If I have multi-axial, I have to change every stress to the corresponding von Mises, whether it's maximum or minimum, and then I can find the mean value and the alternating value. And again, I can use the same technique. I can find the corresponding sigma fully reversed and the mean value. So that's kind of where we are in our calculations. And next time, I think I'm going to cover a little bit more on fatigue and shaft design, because we are shifting now from this week to the next week. We're going to be talking more about shafts and how they're connected to fatigue. So the next time I'm going to stress the subject of fatigue design in shafts, because that's going to be what we will do for the second project as part of it. So what happens is that in shafts we don't have like multi-axial stresses that are very general, but we have multi-axial stresses only like an axial stress due to bending, and we have a shear stress due to torsion. So we have torsion and bending, that's it. And therefore, we're going to find the alternating value of the bending and the mean value of the bending and the alternating value of the corresponding to torsion and the mean value corresponding to torsion. And then our life is going to be easier because we're going to use von Mises type criterion. So this is now the von Mises that I talked about for the alternating and for the mean. And when you plug in the moments and the torque, then things kind of become like this. And then we could use it in design. So I think this is a good point to stop for the review. And then next Saturday, we will pick up here, maybe give a couple examples, and then try to push the second project along so we could do all of the calculations for the shaft lifetime. Okay, so this is, I think, going to finish my formal part of the review, and I wanted to see if there are any questions or concerns or other considerations. Hello? Is everybody still there?
We're here.
Yeah, I can hear you.
Okay. All right, thanks. Good. Okay, so I think I'm gonna stop here and wish you guys a great weekend, and I'm gonna see you next Saturday.
Thank you.
Okay, bye-bye.